Okay, so hello everyone. Thank you for joining this talk, and it's my pleasure to introduce Shehryar Khattak. Sorry for the pronunciation if I didn't get correctly. Dr. Khattak is a robotics technologist at NASA at JPL. So before joining JPL, I was a postdoctoral researcher at the Robotic Systems Lab at ETH, working on the perception, working as the lead of the perception team CERBERUS, which actually participated also at the DARPA Subterranean Challenge. So then clearly he's full of titles and is a really outstanding researcher working on perception. And we are really happy to have him here giving a talk for our lab. So thank you very much once again, and the floor is yours.
Thank you so much for the invitation. I'll keep my video off during the presentation so we can concentrate on the presentation, and afterwards for Q&A, I will turn it on. Good evening, everyone. Thank you for inviting me. As you know, my name is Shehryar. I'm currently working at NASA. And today's talk would be focusing on localization and mapping approaches for especially what are the challenges when doing it underground, and what I will try to rationalize it, like what took it for us to participate in the DARPA Subterranean challenge, which fortunately we end up winning as well. So going through this journey, first I would start with my journey. And so basically, I'm from Pakistan. I started my career as actually a mechanical engineer, and I was not interested in SLAM at all. At that time, I thought robotics was just mostly hardware and control, so I was focused on control. And doing my bachelor's in mechanical, I moved to South Korea to do my master's in control systems in aerospace engineering. And during this time, one day my professor comes in and drops a paper on my desk about SLAM and says, like, look into this field. And I started looking into SLAM and ended up doing my thesis in SLAM for fixed-wing aircrafts. After that, I worked at Samsung in the inspection team, so a lot of computer vision and image processing. So I really got interested in this field, but I always wanted to return to robotics. So I quit my job and moved to US, where I pursued a degree in computer science engineering, mostly focusing on SLAM, and with SLAM, especially in perception degraded environments or challenging environments. And I was fortunate that during this time, the DARPA Subterranean Challenge came along, and I actually got to apply the techniques that we were developing in lab in reality in the sense of competition. And what happened also that because of this challenge, I was able to work with colleagues across the globe in wonderful teams. And one of them was at ETH Zurich, where I ended up moving after my PhD as a postdoc. And I worked there for 2 years, again, gaining some experience with ground robots, especially legged, and also working and leading the efforts for SLAM. And after that, I now moved to California, and I'm working at JPL. I just want to caveat here that all the work that is presented in this presentation is up to my time till my postdoc, and all the subterranean challenge related work is related to, again, my postdoc time, because NASA also participated in independently in the subterranean challenge, but I was not part of their team. I was part of the ETH Zurich and University of Nevada, Reno team. So what is the DARPA Subterranean Challenge? I've been saying that word quite a bit. So DARPA holds these grand challenges, which are typically like 5 to 7 years. And the most well-known in robotics are the Grand Challenge and the Urban Challenge, which actually kick-started or the idea of autonomous driving. So the grand challenge was autonomous driving in unstructured terrains or off-road, and the urban challenge was mostly indoor. And the idea here is to push the boundary of state of the art at that time. And you can understand, like, these were 2004 and 2007, and then the boom of autonomous cars happens 10 years later. So again, DARPA pushing the boundary, foreseeing the future and trying to push the boundary. Similarly, from 2019 to 2021, DARPA announced the Subterranean Challenge. And then the idea here was to push the boundaries of autonomy for underground robotics. So, and the idea is single operator, multiple robots. So humans cannot enter any of these areas. You can only send in a team of robots, and there is a single point of communication as a single as human at the base station. And then these robots have to navigate a variety of environments that could consist of tunnels, which can be man-made, for example, your mines. They can be urban environments, so for example, your subways, and they can be natural environments such as caves. And the idea is that these multiple robots, which are communicating with a single operator at the base station, autonomously explore and try to find artifacts. And artifacts are objects of interest, which will typically be if you were conducting, for example, a search and rescue mission. So for example, if there can be a human survivor, there would be backpacks, there would be communication devices such as cell phones, uh, and other items, for example, fire extinguisher, tools as drills, or cave survivors, for example, a helmet, a rope, which indicates that where the humans can be or where they are lost. And these are multi-kilometer underground environments, and you have to find these objects and report back their location within an error of 5 ± 5 meters. So this was the idea of the challenge. So what is the challenge underground? To motivate this, I show this video of one of our robots during one of our missions or tests in an abandoned cave. And right off the bat, from perception side, you see that this is a completely dark environment. The only illumination there is carried by the robot. You also see that the ground is quite wet. So not only it causes reflections in the visual domain, also LiDAR can have reflections. And as the robot interacts with the ground, it actually slips. So the measurements coming from your IMUs, encoders, they can also have noise in them. And then the robot can also get stuck like this, and your kinematic odometry can drift. However, you can say like Shehryar, some of these problems are just because the robot is interacting with the ground, and that I would agree on that. But if we take a flying robot that doesn't interact with the ground, you can see we have another whole set of challenges. Here we are in an underground mine in US. It's an active gold mine. And what you see is that as a robot flies, we have a lot of obscurant in form of dust. And then this is again degrading your LiDAR and your visual cameras quite a bit. So given these challenges, we can actually like categorize them. So these are all GPS denied environments. Most of them are completely dark. There can be obscurants. So these can be dust, smoke, fog, depending on the scenario. These can be very low temperature environments. So there can be some structure, or if they're abandoned, they can be like of the same temperature. And if you're using something outside the spectral visual domain and sensing, there can be flatness. For example, there can be thermal flatness. And then most of these environments can lack structure. So they can be tube-like, so self-symmetric. And if we combine the last four challenges together, they combined present a set of perception degraded environments. These are the challenges that you typically see in a perception degraded environment. So what do we need? So what we need is resourceful robot localization. And the most important word here is like, what is resourceful and how do we define resourceful? So over the years, our definition kept changing, but we defined a set of characteristics that are required. So first of all, your algorithms should be robust. There would be adversities in the environment that you have not foreseen, that you have not modeled for, you have not accounted for. And your core algorithm or set of algorithms should be robust, that if some additional noise happens or your correspondence search fails, etc., the algorithm itself should have some built-in robustness that it can actually either reject that or still keep working. And then the second thing is resiliency, that if your system is composed of subsystems and some of those subsystems fail, either they can recover or other subsystems can aid recovery of other subsystems. And this brings us into the idea of redundancy, that overall your system should never fail. The subsystems are allowed to fail and they should be recovering, but overall there should be no loss of information at the system level. So for example, for a robot, you should always have a pose estimate and you should always have a map. And finally, that if this resilience is working, how reliable is it? If all systems are working, what is your accuracy and consistency? And if some subsystems have failed, how much have you given up on that accuracy or that consistency of your, for example, pose estimation and mapping? And if we combine all this set of criteria together, we define it as this system is resourceful because it's doing all these together. So in this definition, the whole goal of this talk would be that how we can enable resourceful robot localization with specific focus on perception degraded challenges. So I'll walk through the journey that how we built our system and how then it led to the DARPA Subterranean challenge and the performance in the DARPA Subterranean challenge. So starting off, we started with our first challenge, which is complete darkness. So how do we navigate in the dark? So we took the approach that the humans would take. Let's bring a flashlight with us. So we built a system of a pair of stereo cameras with shutter synced LEDs and synchronized IMU. And the idea was, can we navigate in completely dark environments? And because we are limited by the illumination range and we want to do mapping, we actually put also a 3D sensor, a time of flight sensor, so we can have some depth information. And using this sensor, we were able to navigate, map, and explore an underground mine. So this is Virginia City in US, 12 a.m. at night, and this is a railroad tunnel. And what you see here is that a robot is actually able to plan. It's slowly increasing its frontier and moving forward. However, one problem you will see right off the bat that the range of illumination is quite limited. And this is because you cannot carry more powerful LEDs on board because you're limited by the battery capacity. So you are only navigating, planning to the edge of the boundary and slowly moving forward so that your exploration speed is slow. However, in the depth domain, what you can see is it is beyond your visual range. And the idea would be that can we use this or exploit this to improve our localization and mapping. So we focus on this direction and we try to do fusion at a lower or a feature level in vision depth and try to extract the complementary and mutual nature. So on the left column, what you see that, for example, there is some complementary information. In the visual domain, this poster is really good information in terms of intensity. In depth, it has no information. But if you turn off the lights in the same scene in the right column, you will see that the poster is now offering no information. However, the chair, although it has no information in the intensity domain, it's still something in depth. However, you will also notice that this is also mutual information, that in depth and vision along the edges, the intensity and depth edges meet. So how can we exploit this mutual component of information? And what we did, we actually used a post-estimation approach where we carried a descriptor which is not only represented in the visual domain but also the depth domain. And the idea was that because it's a combination of vision and depth, if we move from a brightly lit environment to a completely dark and come back, the information in the descriptors changes over time, but we are still able to track the feature. So we don't have loss of tracking, and we are able to navigate in and out of lit, illuminated, and dark environments. And using this, we were able to showcase this. So we have our test arena, we have our flying robot, and some part of the arena is lit. So you can see in the RGB frame, like the left portion, it has some illumination. And as a robot navigates in this environment from the illuminated area to the dark area, it doesn't actually lose any information, but it changes the information in the descriptor. And because of this, it is able to maintain consistent tracking of its features. And what you see on the bottom right is that we are comparing the pose estimate obtained on board in real time from the robot compared to the Vicon ground truth system. And now the robot is in the completely dark area. RGB frame is almost non-informative. Depth information is there. As it's moving backwards, it sees more of the RGB. Again, the descriptors are now slowly changing, and then they're accommodating both information from visual and depth domain. So here we see like, okay, depth can work. Only thing is the range of the depth is limited. So why not just use LiDAR, and then all our problems are solved. this has a small problem. So how we showcase this is that we have a small experiment. We are in our arena, and what we do is that we put a large plank of wood in the center, and we started filling this arena with artificial fog. And we have two type of off-the-shelf lidars. So we have the Velodyne VLP16 represented with white points. We have the Ouster 64 beam represented with colored points, which is a visual camera and a thermal camera. And as you see that as the fog gets dense, we have lost all observation of the plank in the visual domain. In the depth domain, where there were so many points, now almost all information is lost. However, in the thermal domain, we still see the plank on maintenance observation, which again motivates us that we should be relying on multi-modal sensing and actually expanding our canvas of the sensors that we use in our system. So again, taking motivation from our previous work, we wanted to again combine visual and thermal to do pose localization. And the idea here was that in areas where we have illumination, vision provides very rich intensity information. However, it is limited by the range of illumination. And if there are obscurants such as fog or dust, it gets blocked. Thermal, it's very good at long ranges, doesn't need any illumination. It's not corrupted by some obscurants, for example, dust. However, it is very low contrast information. So how we can combine them? And the idea is that to still maintain real-time pose estimation. So what we did, we said, like, instead of using the whole images, why not just pick and choose parts of the images and then only do tracking in those informative images. And what we do is that we try to understand the quality of gradients in these high level or larger scale boxes. And the idea is that if we extract features from these gradient rich areas, their descriptors would again be gradient rich, and hence they would be easily trackable. And then we track these larger squares, and not only in the spatial domain, but in the temporal domain. So we can also able to reject things like, for example, dust, what you see here with the red squares on the right. So taking this, we did another experiment. Again, our robot takes off in actually a lit environment, but full of fog. And you can see on the right, you have the thermal image on the top and the visual image on the bottom, and it is trying to select all these informative regions. So most of the informative regions selected in vision are visually rich, whereas in thermal, it's like long range, which is more obvious in this second experiment, where we are in an underground mine. The vision cannot see it till the end of the tunnel because of the limited range. However, thermal can do see it and provide us with some long range features, whereas vision can track features that are nearby. And then again, because of our temporal tracking of this image information, we are able to reject in vision to make it even more robust. We didn't have absolute ground truth in this environment, so we hand measured and put these pole markers in 50 meters, and then compared the you see this pole marker coming up, and then we compared where it is in this experiment and compared the poles with the robot. This is good. We have vision and thermal, they're working nicely together. But what happens when one of them completely degrades? So we know that vision works alone quite nicely. Does thermal alone work nicely too? And is it equally good or reliable as vision? So here's an example. Before the robot takes off, you can see the visual and thermal domain both have information. But as the robot proceeds and we see more and more obscurants, there is a point where visual information is just completely degraded, and we have to rely on thermal alone. So is thermal inertia alone reliable equal to vision, or do we need some modification of the approach that we want to deploy? And given this, we first need to understand that how thermal cameras operate. So thermal cameras, especially in the long wave IR, they report seen irradiance. So this irradiance or radiation given out by or emitted by the objects in the environment. And typically thermal cameras, because they're made for industry, they need to report like large range of temperatures. So from -25 Celsius to 125 Celsius. and at typically at a smaller resolution. And because of this, they are typically not giving out data in 0 to 256 as our 8-bit information as our intensity images, but they report in 14 to 16-bit. So the first thing would be that if you want to use visual techniques, why not just simply rescale them to 8-bit? However, this has some problems. For example, if we do a simple rescaling, as you will see that the image becomes uh, inconsistent. So there is some flickering. Second problem happens is that even if we like fix the noise, fix the scale, that what is temperature range we are interested in, thermal cameras suffer from noise drift. So over time, it will accommodate noise, and because of this, the whole range will drift. And what you would see in the center image is almost a whiteout of your image. To fix this noise, thermal cameras actually do what is called a flat field correction, which is a physical shield. That is, the camera like puts a physical shield in front of the sensor and recalibrates it to re-estimate the noise and then correct for it. And during this time, it has like half a second of or up to half a second of data interruption. So again, all these things combined together have image consistency or loss of image consistency, which have to be taken care of before we design an approach for it. Our key insight came from that don't scale the data, operate in the full radiometric range. And how we show this is like we have two images, one after and one before the flat field correction. And if we just simply scale them, you see there's a lot of visual difference, or they're quite different consistency. And if we plot their pixel-wise intensity difference, we see in the 256 bit or 256 256 range or 8-bit range, we have a lot of spikes in higher intensity differences. Whereas in the full radiometric range, most of our errors are near zero. So this noise, if we scale it, it gets amplified and then it destroys the consistency. However, if we operate in the 16-bit range, the noise as compared to what the data is actually remains actually quite small. So it's better for generalizability if we operate in the full radiometric range. Based on this, we designed an approach which we call keyframe thermal inertial odometry, and we designed a front end which did data association similar to, for example, Lucas-Canada algorithm or direct methods, and it circumvents rescaling problems. So we minimize directly the radiometric errors in image scale space using an image pyramid, and directly trying to align images in the spatial and temporal domain. And what this enables us is operational generalization. We can operate in any environment without knowing what is the highest and the lowest temperature in that environment, as long as it is in the range of the thermal camera. And then on the back end, we chose for an optimization based backend, which again does alignment with previous keyframes chosen in the temporal, so like last two keyframes, and spatial, which are again more distributed in terms of space. And this gives us resilience against data interruption. So even if the data gets interrupted for half a second, we still are able to operate and maintain our pose estimate or remain consistent. So we did a indoor experiment, again returning to our arena, this time completely in dark. We put some objects that are emissive. For example, we put some wire, a space heater, a computer. So objects of different temperatures. So we have different temperature ranges. So the camera can come into the camera field of view, exit the field of view, but we can still maintain tracking. So what you can see here, flat field correction is happening. However, our matching doesn't care. The frames, so frames here are shown in 8-bit. So for visualization, their appearance changes. However, tracking remains robust. And what we show here that our algorithm maintains pose estimate consistent with the ground truth. We actually try to adapt state-of-the-art visual approaches and show better performance. However, just to clarify, these are state-of-the-art approaches for vision. They were not built for thermal domain. And our only point here is that we need to go back to the fundamentals to build approaches for thermal domain rather than just blindly applying visual domain approaches that are already out there. So these are again state of the art in visual domain, and they still perform amazingly in visual domain. We also took the same approach and applied into a real world scenario. So we have an underground environment. Again, this is an active gold mine, and this is a completely autonomous mission. So the robot is planning and exploring for maximizing its exploration or information where it can improve the observation of the environment and map it. And on the bottom left, you see our keyframe to current frame matching, whereas on the right you see is that the yellow estimate is ours and the green estimate is coming from the LiDAR on the robot. And what we can show that even we are going through this high dust area, we are still maintaining our pose estimate similar or consistent with the LiDAR. We go into these areas which are again very wet, so they have very small thermal thermal gradients. However, again, we are maintaining information or tracking information in the full resolution of 14 or 16-bit. So we are still able to track features even in these very low informative regions. And as we move forward and go into areas which have, for example, a power generator, and now this is a completely different temperature range from the rest of the environment, we still are not like the rescaling problems don't happen, and we're still able to maintain our estimate almost near to what the LiDAR can be. So this is good, but then the question arises that, well, LiDAR is working. Why do you need this? And this is true. If you want to do large-scale mapping, LiDAR is an amazing sensor, and we have used it. For example, in here, what we see is that we put our we put a LiDAR on top of a underground vehicle, and we're driving around in this underground mine. So here, this one is the point cloud, colored point cloud around the vehicle, and then we drove about like 1.7 kilometers, and we were able to map like the multi-level mine with LiDAR. However, every sensor has its limitations, and if we go into an environment, for example, it's an underground pass, which is again self-symmetric, and well, you can see it's like a tube-like structure. So what happens is the optimization-based approaches that minimize distances for LiDAR scan to scan or scan to map alignment, they become degenerate. So they cannot, so it's a fitting problem, and as soon as you're encompassed in this tube-like structure, the point cloud that is coming a step forward or a step back, it looks the same, and what happens is that you start sliding. And here is what you see here is a manifestation of this, that our robot is thinking that it's stuck in this position, whereas from the video it is quite observable that we are consistently moving forward. And as it reaches the end of the tunnel, it now has like more distinct features in the environment, and escapes it. So suddenly it starts working again, and the robot starts moving forward. However, you can see that the map is not correct, and it's like sort of it's broken. So our solution to this was a multi-modal approach. So we wanted to combine all the lessons learned and from all this development and how to combine them. And then we came up with an approach we call Complementary SLAM. And the idea here is that we have a flexible approach, that we have estimators running in parallel. And in parallel, so if a subsystem fails, it can either be recovered or the overall system actually doesn't lose any of its reliability. And the second thing was that instead of just fusing all the estimates together and spitting out like one estimate, we wanted to do it in hierarchical fashion. So we started with an IMU. The IMU gets fed into the visual thermal. The visual thermal gives us a pose estimate. Pose estimate is then provided to the second set, which is LiDAR odometry. Just scan to scan refines on top of it, and then this LiDAR odometry goes into LiDAR mapping, which is a scan to submap approach. And then the idea here is that the pose propagates from left to right, and at any point, if you have some error, it has the chance to recover the pose from the previous estimate. And how do we judge this? So we have a bunch of data and estimation level checks. So data level checks, for example, in the visual and thermal domain, what we saw were these image quality metrics. So we were doing spatial entropy, and we try to understand that how much information we have, if we are getting a point cloud, and if the point cloud, for example, is in a dust cloud, only around the robot. We understand that we are in when confined region or something has encompassed in the LiDAR so that we cannot see further. So we can understand that the sensor level checks have failed. Secondly, we have estimation level checks. For example, if we check the health of our optimization, we check how the what is the size of the eigenvalues of the Hessian matrix, and then based on that decide that if the optimization is healthy or not. And if the optimization is not healthy, we actually reject that estimation and try to fix the degenerate direction with opposed estimates from the previous approach. So again, the idea of the approach is that you always go from left to right. You will always have a pose and a map at the end, and you get a sensor estimate. You get a pose estimate that gets refined as you move through this chain. So taking this approach and applying it to, again, the highway underpass, and again the original on the left, and on the right what you see is our proposed method. And just in interest of time, I'll just show the final result. So this is what happens. You see the map is broken with LiDAR only approach, again because of the same problems I mentioned, cell symmetry, degeneracy and optimization. Whereas with the proposed approach, when it's trying to understand that it is failing, it can actually switch to another sensing approach and fix the degenerate direction. And then the whole map becomes consistent and the robot keeps forwarding as it should be. So this was our approach, complementary SLAM. And then at this point, we took it to DARPA, and this is what we applied in the DARPA challenge. So what was the DARPA challenge? So the finals of the DARPA challenge happened last year in September 21 at Louisville, Kentucky. And they built a whole underground environment which had segments from all courses. So they had the urban, the tunnel, and the cave segments, again, fully man-made. So they took 8 months to build this elaborate course underground, or an elaborate playground. And the idea was that can you search, navigate, and autonomously find those artifacts, and for each artifact you get a point. Maximum points were 40. The team that scores the highest point the fastest at the end of 1 hour run wins. So what challenges did we see during this our finals run? Sorry. So as I said, I was part of Team CERBERUS. So this Team CERBERUS was a collaboration of University of Nevada, Reno, where I did my PhD, at Zurich for my postdoc, and then we had Oxford, Berkeley, and 2 corporations, Sierra Nevada Corporation and Flyability. And CERBERUS, although we were motivated by the name of the Greek the Greek dog that guards the underground, actually it's an acronym and it's a mouthful. It's a collaborative walking and flying robots for autonomous exploration of underground settings. And we had a set of robots. So we had legged robots, which was our main explorer called Animal. We had our scout aerial robots. And then we had roving platforms which were tethered to the base station and actually didn't help in exploration much, but were actually carrying a huge antenna and improved the comms provided underground. So just to see like what our system was, so our Animal robot was the most capable robot and had a bunch of sensing on it. So it had thermal, visual cameras, LiDARs, joint encoders. So it had kinematic odometry, so the complete sensor suite. So it had visual, thermal odometry, LiDAR odometry, kinematic odometry, and also it had a larger compute budget. So it had a laptop class computer on board. We had our flying robot, which were our middle class, our scouts, which had again a reduced sensor set. So for example, it had 1 visual camera, 1 thermal camera, 1 LiDAR, and then had a mobile class, so Intel NUC on board for mobile class processing. And then we had our really small collision resistant robots, which only had an IMU, a LiDAR, and a visual camera. And then this also had ARM processor on top, so again an embedded class. And the idea was that this approach that we built, CompSlam, it is again because of its modular or flexible nature, you can pick and choose what you want to run on each of these robots. So it will work across all these robots and across these different sensing, availability of sensing, and you can choose these all modules and they glue together, and then again they work on all laptop, mobile, and embedded class. So again, the flexibility is to flexibility is to help with the diversity of the across compute and sensing capabilities. And then during the challenge, we also had a server which would listen to all the information. So each robot ran a small set of ran its own ComSlam, but then it would send the submaps and artifacts to a ground localization server, which would try to combine the maps together by finding intra-robot constraints. So this was the idea. However, as I said, during the competition was a 1-hour run. As the maps grew, our optimization became larger, and we weren't able to converge on the base station side. However, due to some quick thinking of our operator, he switched to like robots individual solutions and reported again the artifacts in their own using their own localization for each robot. So looking at the environments, so these are some instances of our robots during the very final run. So what we see is that there are instances of complete darkness, where a robot is navigating through a cave environment. There are environments which have lack of texture, so very smooth walls, white and dark. So here the multi-robot mapping approach had the biggest problem because the visual constraints were not good enough. Then you have these confined environments, which again, your LiDAR point cloud will suddenly shrink and you will only see a part of the environment. And then you had these problems where, which were very rocky or rough surfaces, and the robot was slipping, and you would see a lot of shocks and jerks on the encoders and the IMU. However, my most favorite part was this, and that was that robot was actually navigating through a section of the environment, and DARPA was very clever, so they hit some trigger switches, and as it moves this environment, suddenly the whole environment gets engulfed with fog, and well, you can understand that the visual cameras and the LiDARs are degraded. However, we were able to detect this and get out of this without a huge break in our localization and mapping. So these are the 4 robots. So our robots were named Chimera, Cerberus, Camel, and Cayman. And in the background, you see the ground truth environment, which was provided by DARPA after the challenge. And what we do is that we try to overlay our maps on top of them and how much each robot explored. And combining those maps and the number of artifacts that we provided. So these are the different, again, color coded by each robot, that how many robots found which type of artifacts. And in total, we were able to detect 23 out of 40. And luckily, this gave us the highest count, and we were able to detect it the earliest. So we were able to win the DARPA Subterranean challenge, which was a very fortunate and fortunate thing for us. So concluding lessons learned, robot perception, even though we did win the DARPA challenge, it is still a very hard problem. And as soon as you switch your domain, there's a whole set of new challenges that are waiting for there. So think of navigating in forests, think of navigating underwater, and even harder, like think of navigating on icy surfaces. So for example, in Antarctica or icy moons, which are quite challenging for the sensing we use. So we have to be creative and understanding of the challenges of each environment. So again, it's a very active field. One solution that we found that worked for us was multimodality. You don't rely on one, but a set of sensors. And this actually improves the resourcefulness of your system quite a bit by providing resiliency on different levels. However, this is still an active field, and how to use sensors and what to use is still an active problem. So here, what I show you an example is this navigation in forests, and now you can, there is some sun glare, and because of the sun, you can't see this part of the environment in the red, and there's a tree hidden there. The interesting thing is in the LiDAR, because there is shrubbery around the trees, you can't actually see the tree trunk very nicely in the depth domain too. So if you have a range image, you can't see it. But there is always this complementary or auxiliary information, for example, in terms of intensity of LiDAR. And here you can see the tree trunk quite nicely. So how to use sensing and how to exploit it, what different information is coming in, is still an active field and requires fundamental work on algorithm development and understanding what the sensor provides and how it senses. So this can provide resiliency, but requires fundamental work that's still going on. Is that in DARPA, we were relying on, for example, health checking, a set of hand-tuned heuristics. And our solution was we tested across multiple environments, and this improved and we converged on a set of parameters that work across a broad range of environments and also the finals. However, the heuristics are always a limitation. So as soon as you change environments, there would be something new that you haven't modeled for heuristics. So one way to move forward, and this is something we just got accepted at IROS, was to use learning-based approaches. That what we showed here was that we actually trained our trained a network which was completely trained on simulation data, so we can simulate arbitrary environments, and it would try to predict if the scan-to-scan matching or scan-to-map matching will fail or not. And just by looking at the point cloud, it can tell you directly, hey, these directions are not localizable. For example, if you are in a tunnel, as a human, you will know that, hey, the forward direction aligned with the LiDAR is non-localizable, but you don't know until you reach optimization and check with thresholds. The network can become smarter, and it can tell you that. So this is, again, one way of getting rid of these hand-tuning heuristics. And last, that large scale. So it's, again, onboard localization is fine, but when you have tens of robots or even more, hundreds of robots, it requires a different set of sensing, and then your problems become a magnitude harder. So in the DARPA, we saw this firsthand, that our multi-modal approach, our multi-robot approach failed because we ran out of time. However, this can be critical in more real-world applications, for example, autonomous driving across multiple cars. Finally, I would say, again, a lot of work I presented here is in the localization domain, but to win the challenge, there are so many fields to enable robot autonomy. So controls, path planning, artifact detection, reporting, UI, and a lot of engineering. And I'm very thankful to have an amazing team to work with over the years. And with their contribution, we were able to perform well in the DARPA challenge. So a huge thank you to them. And also a huge thank you to all the robots that we deployed in the competition. Most of them are not perfect. There's some hanging duct tape there or some zip ties there, and well, a lot of them have replaced parts over the years, but they taught me a lot and were facilitating my research. So a huge thank you to them. And with this, I conclude my presentation, and I would be happy to answer any questions. Thank you for listening.
Thank you very much, really, Shehryar, for this incredible, nice presentation. So thank you very much for the this great introduction to your work. So I think that we can open up the question and answer time. So anyone who would like to jump in, do not hesitate to open your camera and ask your question. You can book the question with the raising your hand button. So yes, Silvio, you want to jump in? You are on mute, Silvio.
Yes, at the moment I don't have any question.
Sorry, I thought that you wanted to intervene. I mean, I have a couple of questions so the first of all, I mean, at a certain point you were able to detect the fog inside the tunnel. So this was a little bit amazing. How did you detect the fog? The fog directly from vision, or what was the strategy to detect the fog?
So we are not essentially detecting the fog, but the effect of fog. So, for example, in vision, what we would see, as I applied here, what happened because the fog areas have low gradients, we would stop using those parts of the image.
I understand.
And over time, what will happen is that these number of green boxes will become lower and lower and lower, and then it will not use it at all. In LiDAR, what will happen, as I showed here, if I play this video again, as the fog gets denser and denser, you will not get returns. So if you're checking the number of points in your point cloud, you will see at some point your data level metric will say like you don't have any information, so don't trust this sensing. So at that point, what happened was like both vision and LiDAR, when the animal walked through the fog, they both said like, yeah, don't trust us, our data is not good. Thermal and kinematic were still working, so we proceeded with that.
Okay, that's pretty much clear. Yeah. Okay, I also had another question. I mean, the concerning the environmental condition inside the tunnel. So, did they change considerably? Like when I don't know. I am assuming if the fog arrives, then the densities of the air changes. Then the lift forces of the propeller somehow change. So all these things have to be compensated for by the controller. So I was wondering, the temperature, for instance, the temperature was a little bit, I mean, more or less constant during the path. The densities of the air was a little bit constant, and how and if these parameters were taken into account for the controllers, or you simply say the controller is robust enough, for instance, for the quadrotor, and then the attitude controller is going to compensate for that.
For typically for real environments, for example, tunnels and stuff, again, we were testing in a portion of the tunnel, right? So for there, and a flight of is like 10 minutes. So you just have 10 minutes of flight. So you go like 300 meters in that time. These small sections typically had similar conditions. During DARPA, so even if you think of real life, like if there is fog, then this will be fog all over.
Okay, I understand.
Right? In DARPA, it was different because you had these triggers that would just introduce fog suddenly. Right? However, like this was like such a small change, or happened by the time like it was happening and your robot is moving, you are sort of like escaping it. It wasn't that difficult for the robot controller. So I think like the control is so robust now that these changes are so small as compared to what is happening in the environment, they like actually didn't matter.
Okay, so the robustness of the controller takes them into account automatically.
Yeah. And I think that differences is like quite small because fog, by the time like the fog fills out and again it's like a pocket, so our flying robot has like passed through it as long as it has a state estimate to actually keep on moving. So that's why.
Okay, that's pretty much clear. Any question from the audience?
I actually would have some questions.
Yes.
So first of all, thank you very much for the presentation. That was great. First of all, I was curious about the preparation. Let's say, how did you prepare for the competition? I guess that you mentioned that they spent 8 months to prepare the course. So I guess you weren't able to access the course beforehand. So how did you reproduce part of it in your labs? I don't know. You mentioned you were testing in Virginia in some railroad. So it was kind of interesting for me. Like, how did you prepare for the competition?
That's a very good question. I mean, this was a 3-year-long competition, right? So we started testing like we only we just knew it was tunnel, urban, and cave, and but they never told us like before 3 months where the competition would be held. So we have no idea where this would be. And the idea was that lot of field testing. That's the basic thing. So we were going to a lot of mines. So we were just imagining scenarios. Okay, we need caves. So we were searching caves in Switzerland, trying to do tests there. Urban environments, we would test in like our building corridors. Like typically under the building, you have a lot of these access tunnels. So you would test in there. So I think overall, like if there were like across the globe like 20 or 30 environments that we were testing. or we tested over 3 years. But the most important thing, more than that testing, is your own synergy with the robots. And that, what I mean is, like, every week we would do almost a shakeout. So we would do like go to the basement, do a 1 hour shakeout with, like, okay, we have an animal robot, we run the full stack, whatever it is. And we tried to do a small mission. Like, although the final DARPA is like 1 hour, we did 15-minute mission. And what did this trained us for was how to set up the robots quickly. What is the operator doing? What is the what is the operator doing? What is he setting up? What is the safety operator for the robot doing? How is he starting the robot? And what are the kinks? Like, what are the small things that are happening here? So, for example, oh, comms don't work when we turn on power like this way. Why? Okay, this can be the problem. The algorithm challenges were like coming on larger scale. Like, you would go to a new environment, you would discover some algorithm challenges. These were like during large tests. But a lot of the system efficiency tests were on these small scale integrations that you were doing in your like weekly shakeouts. We store them, and then we would continuously check them. And then this would actually help us with like small tunings. For example, in this corridor, this thing is failing. You have this new feature. Did it work or not? So these were like system tech, and then large problems would happen, like, oh, we went in this one, the environment was completely changed. So for example, if you go from a very small scale environment to a very large scale environment, maybe the parameter set you have set for the small environment won't work for the large scale environment. And now this will force you to do generalization. So I think this was a combination of these two type of tests that helped us a lot. So these large tests across environments over the years, which are also expensive because you have to travel a lot, you have to transport the robots, but these small tests I think were equally important, and that made us efficient in terms of like how our robots can be turned on, and like we can go for a mission in 30 minutes. So I think these two things went in synergetic way.
Yeah, that's very clear. Thanks a lot. That's great to know. Actually, that the whole approach is very important for us. Thanks.
Any other question from the audience?
Yes. Sorry. Can you hear me?
Yes.
Okay. I am Gabriele Nava. Thank you for your presentation. It was very interesting. I'm here in our experiment area with the Iron Cab robot. I don't know if you can see it from AFAF webcam. We turn it on now. Okay, so we followed your presentation. It was very interesting, and we found out that a lot of problems that you mentioned are similar to what we are also facing for trying to make the robot fly. In particular, we are trying to find a way to estimate the base position and orientation of the robot during flight. So it seems that your fusion of different sensors was a very good idea, but what would you suggest for our specific case? So instead we fly it outside, but we also have dust, we have wind, we have other light changing conditions, because the robot also the jets turn around a lot of dust. So the conditions seem not so different. What would you suggest to us?
I think I would suggest look at the data. That is the most important thing. Always a lot of our insights all just came from just looking at the data. And when I say the data, it's just like look at the images, look at their raw pixel values and stuff, and then that gives you actually a lot of insights. Or look at the point cloud and what is the data corruption happening there, and that would guide you a lot. For dust, I think thermal cameras were quite so I mean, again, it's the physical property, so physics is on the top of everything, and this is the property of thermal cameras, that the wavelength is typically larger than the particle size of the dust. if you're outdoors, you also have, I guess, access to GPS, so you're not completely GPS denied. So that will also give you some information, if not fully. And depending on your application, I mean, it's again like it's very hard to give a very generic advice like do this. So it is always dependent on the application, and then just I'm trying to understand like where your application domain is and what you can exploit, and then what set of sensors are best for it. So that would be my advice. Like look at the data, see your application, try to see what you can exploit, and then just try to fuse them. I mean, if you have a specific question, I can like tell you more, but I think that's what I could understand. So if I'm wrong, please correct me.
No, it was clear. Thank you. Thank you. We will for sure try to look at the data and follow your advices.
Any other question from the audience? Okay, so I think that we can stop also the recording.